And so let us move forward to our next invited talk from Ming-Hsuan. And Ming-Hsuan, could you share your screen?
Sure. Okay.
Thank you.
See. Okay. Can you see my screen or?
Yes. Yeah.
Okay. Good. All right. So I probably just stop video to save some bandwidth. Wow. Okay. I just close the video. Okay. All right. So today I'm going to talk about our recent work on.
So we cannot see your screen.
Oh. Okay. You cannot see my screen.
Yeah.
All right. Hold on.
We need to share again.
Okay. Okay, share screen.
Yes, it works now.
Okay, all right, great, thank you.
Thank you.
I have to find this guy here, just a second. All right, sorry about that. Okay, so today I'm going to talk about our recent work on synthesized human image in 2D and 3D scenes. And so the main idea is this. Suppose that we have a semantic map on the left, and we want to insert human or cars into this scene. And likewise, on the right, we have a 3D, we have an image, and we want to insert human into this one. So we need to understand the contents in order to insert object at the right position and right size. And in addition, we also want to generate different shapes or different pose as much as we can. And so if we do not understand the contents or the objects, then the result will be quite strange, right? And here, this will be a giant, and here the human is not supported. So in addition, as I mentioned, we also want to synthesize outputs with different shapes, not just location, but also different shapes. So, and in addition, so for that, we need to understand the context very well. So for example, even we have a vehicle here, and even at the right size and right scale, if we do not know the context, then the synthesized result will be weird. And for 3D scene, we certainly need to know the geometry, 3D geometry. Otherwise, it would be very difficult to insert a human into the scene and have a realistic results. And okay, so in order to do that, we take the idea from affordance. So what is affordance? So basically what it means is that we want to know the functions that objects can be used for and how they interact with the environment. So for example, for this image here, the object of interest are cars and humans, and we need to know where they can appear and how they can interact with the environment. Likewise, for the 3D scene here, we want to know where the humans can stand and where a human can sit. And as I mentioned, we also want to know how they are supported. So certainly the first thing we need to know is where are the objects, where we can insert the objects. For example, here, we most likely will insert humans on the sidewalks and cars on the roads. And likewise, we also need to know the scenes so that we can insert a human standing or sitting at the right location. So in addition, we also, as I mentioned, we also want to generate different shapes. We also want to generate different variation. So for example, here at the one location, we can synthesize different pose. And likewise, for 3D scene, we can also synthesize different person at different posture. And with the right shape, then we can synthesize the contents using image translation methods so that they will look realistic. Okay, so how, and the third question we need to know is how do they interact with the environment, especially for 3D scenes. We need to know the objects and how they interact with the environment. So that we can insert person at right pose and right position and right posture, and they are well supported. For example, we can insert a human sitting on sofa or a person standing in the right area. Okay, so in this talk, mainly I'm going to talk about two recent papers. One published in NeurIPS 18 and the other one CVPR 19. And if time allows, I will also talk about our recent work on synthesized human motion for dances. Okay, so here's the question. So, well, I guess you cannot answer. So, but I still would ask you. Okay, so these are synthesized results. So, which one is the one that, according to you guys, which one is the one that we insert? Which one is real? Which one is the synthesized one, and which one is the real one in the scene? You need a semantic map. Well, I know you cannot answer, but suffice to say, all the results look quite realistic, right? But the real answer is that there are only two of them are real ones, and all the others are inserted into the scene. So what we do is that we learn the conditional VAE on the scene, and then gradually add one object at a time. So for this case, we are interested in humans and cars. So we can insert one human, and then condition on the new scene, we can generate another one, and another one, and at different pose and right scale, and different shape. Okay, so basically we need to add this semantic map, and you may ask why we operate on semantic maps. Well, the problem, the easy question is that the easy solution answer is that it makes the problem much simpler, and we don't need to care about the appearance. And in addition, once we get a semantic map, we can use any image translation algorithm to fill out the contents. And yeah, so this is what I'm saying. So, and in addition, directly operating on the RGB image is quite difficult. And in addition, for some tasks, we do not necessarily need to have, we would rather operate on semantic maps. For example, for graphics design and all that, so that we can apply to different tasks. So this is one, for example, I mean, for game design, once we can insert the semantic map, we can insert object into the scene well, then we can render that easily. So this is why we take the approach to operate on semantic maps instead of RGB image directly. Okay, so the main goal in this work is that we want to know where the objects are and then synthesize shape. So in order to do that, we have two modules for that. One is where module, the other one is what. So let me close this one. Can I? Okay. Okay. Just a second. Okay. So we want to first predict the likely location of the objects, and then we can synthesize. We can synthesize the shape. So, but we want to learn these two modules jointly, and we want to build an end-to-end model for that. And as I mentioned, we also want to generate diverse outputs as much as possible. Sorry about that. There's a spam call. Sorry about that. This is what happened at home. Okay. Okay, so the first thing we need to generate, we need to build a where module. So, well, I mean, you may think that, okay, we can label the data and learn from that. For example, we can ask someone to label data and put some probability of, say, this, with high probability, we can synthesize the object at this location and 0 probability at sky and some probability on the road because people do appear on the road from time to time. But the problem is that it's very tedious process, as you know. And sometimes we don't even have a ground truth. I mean, because it will be very difficult to define the probability. Another way we can do is that we can operate directly on an object. Say we can, given some training data, we can take object and then we can take them out and insert at other places. So the problem with this approach is that we need to identify object, remove object, and append the content. So this turned out to be a difficult problem. And in addition, there are so many data points we can use, so the variation is much less. So the approach we take is to first predict a bounding box where the person can appear. And so there are 2 reasons for that. One is that it's much simpler, and so we can just predict the location and scale. And the second reason is that for the object of interest in this work, cars and humans, they can be enclosed by bounding boxes. But on the other hand, we did not directly operate on XYWH. We do not operate on the location and width directly. The reason being that we want to build an end-to-end model, and this is, if we operate directly on these are not differentiable. So the approach we take is this. So we given the semantic map, then what we want to do is to synthesize. We want to estimate the F1 transformation to take a random box to a certain position, and we want to make sure that is as realistic as possible. So basically we draw a random vector, we send it to spatial transform network, and so that we can transform this bounding box at a certain location through this F1 transformation. And we want to make sure that it's as real as possible. So we found the annotated data with instance annotation. We can take them out and use this to train with adversarial learning. Then we will be able to tell whether the synthesized result is real or fake. So we do that, and then the problem, so these are the results we have. The first result we have with this adversarial learning approach. And so the first issue we encounter is mode collapse. So here, in fact, we draw 100 object location, but all of them appear at the same position. So in order to increase diversity, so the reason being that this random vector is not well trained. So just like many other generative model, we add in reconstruction loss into this framework. So we can add one reconstruction loss to reconstruct this random vector or the bounding box, and either one of them would give us much better result. So by adding this one into the adversarial learning model, then these are results we have. So at least we have 2 modes. So we are doing a better job now, but this is still far from what we would like to have. So we look into that, and it turns out that there is no constraint on the network to encourage, or there is no additional loss to encourage the result to be different. So we only need it turns out that the network only moves the bounding box slightly among all the solutions. So this is why you see, although we have two modes, but the most results are still concentrated at certain modes. So in order to increase diversity, so we add another pipeline with this VAE. So here we can take all the, from the real example here, we take one random vector, and we also learn the F1 transformation such that we can take one random box and transform onto the location. And this both STN share the same parameter. And with this, we will be able to encourage the model to generate position at the different locations. So this is the first one we have. This is adding reconstruction loss. This is adding another supervised loss into this model. And then we have a much better results. So now with this, then we will be able to generate, we are able to generate the position of we can train the what module to insert object at a right position, at a different position at different scale. And we can insert both cars and human. For each one of them, we train one model. And here are the results that we can see how model learns over the epochs. So gradually, the model learns to generate objects at more diverse location and scales. Okay, so once we have this aware module, the next one is what module? We also need to generate shape. So we take the bounding box predicted by the where module, and then we use that and to synthesize shape at that position. So this F1 transformation, so this similar to the previous one, we still take a random vector. We want to generate generator to synthesize shapes, but this position will be governed by the F1 transformation from the what module, where module. And just like where module, we also add in one supervised path in order to encourage model to synthesize, to encourage the model to generate diverse outputs. So here are some results we can see from encoder decoder, and with supervision we can have more diverse outputs. Okay, so the overall architecture is this. So basically we have input, we have semantic input, and we have random vector, and then in the forward pass, then we take one unit box and then generate by using the what module, we will predict one location, and with the shape model, with the where module, we have a position location, and with one module we have the shape, and then we can synthesize one human at one position, and for the backward, so then during the backward pass, then the gradient will be passed through either from the where discriminator or what discriminator, or the arrow pass through this. These two modules are connected by the same F1 transformation, so all the gradient will pass through this F1 transform in the STM model. So we can train both networks jointly. So here are some results that we can see that we can fix where, but then we change what. So at one location, we can generate diverse shape or diverse pose. Okay, so here are some results that this is input, and here are some generated position and shape in this scene. And remember, this is condition. The input is conditioned on the semantic map. And then we can use any image translation or synthesizer for that. So for example, use Pix2Pix HD, and then we can from this image, we can synthesize real output. And here's another example. Then we can insert object into the scene and then render the real output. Notice that here we do not use any branding. We just straight up just use since translation or any gun using cycle gun or any other method for that. So you will see that the position looks realistic, but if you pay attention to that, you still see there are some the results are still somewhat odd. So here's another quiz, is another question for you. So among all these image, among all the humans or cars, which one is real? Which one is real? Which one is not? So you probably can see that. Okay, for this example here, this one is a synthesized one. So it's not too difficult to see this because the render result is still far from realistic. I mean, without branding. And here we insert non-human, but at least they look as realistically. I mean, they look as realistic in the sense that except the lighting and except lighting, otherwise it looks pretty reasonable. Okay, so here's another example. Another one. Okay, and we did some user study to evaluate whether the system is good enough to fool human or not. So given a pair of image, one is real, one is fake, and we ask user to tell which one is real, which one is not. And so there are 50-50 chance that human will make a mistake, and our result receive 40% well, chances to be real. So it does a decent job. And we also along the way, we also have a different baseline for that. And for details, please look up our paper and supplemental material. And okay, so to summarize, in this work, basically we have two modules. We have one where module and one module to predict position and shape. And we train them jointly, and these two models are connected through one F1 transformation. And therefore we can learn them jointly. And yeah, so that's what I want to say about the 2D scenes. Now for 3D scenes, we have to do something more. And I have about 10 minutes. Well, I have another 20 minutes. Is that right? Yeah, almost 20 minutes. Okay, I'll be quick. So for 3D scenes, then what we want to do is we also need to learn the 3D. We need to know what's in the scene so that we can decide whether a person can sit or stand. And the 3D affordance can be used in medicine for robot scene and game development, so on and so forth. So the main thing is that given one 2D image, we want to insert 3D, we want to insert a human into this scene so that the result would look realistic. So for example, we can insert human standing or sitting. And for sitting is we want to generate humans that can sit on a sofa or sit on a bed. Okay, so so in order to do that, we need to generate results that are semantically plausible and physical stable. For semantically plausible, meaning that okay, the action should be common in the scene. For example, we don't want to generate humans sitting on, say, a TV or standing on TV. Instead, we want to have humans sitting on, say, sofa, on bed, and standing on some area without any furniture. So in order to do that, we have to, from one 2D image, we have to incorporate both semantic knowledge and geometry knowledge, 3D geometry. And we need to use both so that we can synthesize humans in these scenes realistically. So the question is whether we can develop a data-driven model for that or not. And yeah, the answer obviously is yes. And so, but the problem is that there is no 3D affordance data set that we can learn directly from. So instead of doing that, we use one 2D affordance data set and one 3D endorsing data set, and you use both semantic knowledge from one data set and 3D geometry from the other data set and integrate them together. And the approach we take is that in the stage 1, we build a 3D pose synthesizer to construct a large data set. And once we have that data set, so that we can learn the 3D, so that then we can train the data-driven, then we can train a model just like the previous work with where and what module, so that we can insert a person in the scene realistically. Okay. So as I mentioned, so there are no 3D affordance data set that we can operate directly. We can learn directly from. But fortunately, there is one 2D affordance map, 2D affordance data set available, and there is a 3D data set available that we can use. And so the question now is that how do we integrate what we can learn from each one of them together for the task? Okay, so for the 2D affordance map, for a 2D affordance data set, we can learn the heat map where one can stand or sit. And so this has been studied. But the problem, so so the first thing is that we need to learn a model, so we can do that, and then we can use that and apply domain adaptation to a 3D scene. Although the structures look similar, but one is real, the other one is synthetic. So there is a large domain gap. So we need to find a way to transfer what we to adapt the model. And once we have that, then we can project the 2D pose into the 3D voxel, and then we can determine whether the 3D pose is realistic or not, meaning that whether we want to know whether the 3D pose intersect with some furniture or not, or can sit on some furniture or not. And then if necessary, we need to adjust the position. Okay. So the first thing we need, as I mentioned, so the first thing we need to learn is to learn the heat map from 2D affordance map. And so we use an encoder to do that, and then learn from label data, we learn where the person can stand or sit. And so then we can synthesize, we can generate pose for that. But now the problem is that now this has been done, so I don't need to talk too much about that. But the problem is that for 2D scene, for these two data sets, there's a large domain gap. So we have to apply one domain adaptation method on the feature level so that we can adapt one model to the new scene. So that given the 2D scenes, we know where the person can sit or stand. And then likewise for this CG3 Sun data set, then we can generate heat map so that we know where a person can sit or stand, and so on and so forth. And then so that we can bring a person. So we can bring a person from 2D scene to 3D world. And so with a camera parameter provided by some some data set, then we will be able to project the person from 2D to 3D world. However, we also need to know whether intersect with we also need to have depth in order to map 2D pose to a voxel well. So in order to do that, we sample we assume that human height is about 1.7 meter high, and then we can draw a sample from that, and then from similar triangles we can estimate depth, and from the with the estimate depth, then we can project the 2D pose to 3D scenes. And then we have to then once we have a 3D pose, then we have to see whether this is physically feasible or not, because we need to know whether the person intersect with the furniture or not. For example, if we do not consider that, then human can easily intersect with the furniture. This is physically not possible. And if so, then we have to adjust the position to the nearest location that without any interference. Okay, so in order to do that, there are two rules that we follow from in the literature. One is free space constraint, meaning that where we can put the object, and the idea is pretty straightforward. So we take a 3D pose, and then we know the 3D scene structure. We take correlation and figure out where there is no correlation, or whether there is correlation or not. If there is correlation, then that means that we cannot put a human there, and otherwise we can. And the other things that we also need to know where the person can be sit, and so then so basically we know the furniture again. We apply a 3D Gaussian on top of that before we apply correlation on that, so that we can determine whether a person can be supported by the object or not. Okay, so once we have that, now we have we can construct 3D. We have a fully automatic 3D pose synthesizer. So this is the first step that we need in order to build a data-driven, in order to synthesize pose from one in an image. Well, this is the first step we need to do, and so that we can generate a lot of 3D poses in the scene. So here are some of the results we have. So then in a 2D image here, then we can synthesize 3D pose with right pose and with physical support. So we generate about 1.5 million poses for that. And then, so this is the first step we need to do. And from that, then we want to learn then the rest is similar to the prior work that we need to learn. Once we have the data, we have ground truth, so-called ground truth, then we can train the where and what module for that. So given the time I have, I'll skip some of that, but the ideas are pretty similar. We need to train where and what module, and we need to use reconstruction error and KL divergence, and all that for to determine, given one 2D image, how we draw samples so that we can insert a human in the scene, and then generate different pose. And for details, please refer to see our paper, and then we use both 2D pose and also 3D geometry, and also KL divergence for regularization. And the what module is also similar to the where module, but with different losses. Yeah, basically the second part is similar to the first work I described. Okay, so I have a few minutes left, so I'll just speed up a bit. Okay, so once we have, so then again, this is similar to the prior work that we have a supervised path where we can draw sample. So that given a scene, then we can draw sample, and we have where and what, so then we can generate a person in the scene. Oh, sorry, this is with supervised pass and this is unsupervised pass. This unsupervised pass is both are similar, except I flipped that in this part. But the architecture is similar to the prior work. Okay, so yeah, so basically our 3D pose prediction model introduced where and what module, right? And then we test whether it's a whether we train the classifier to see whether the generate 3D pose is plausible or not. And so for that, we train the classifier with pose we have, and then we label some negative examples. Those are uncommon or impossible poses, and then just to see whether this given a pose, then we will know whether it's plausible or not. And we compare, so we compare with baseline model in the literature, and then for detail, you can see our paper. And then our model can take RGB input, and also in addition, we can also take RGBD or depth input. For detail, I can see the paper. Okay, so I'll skip this, and then I have a few minutes time. Okay. All right, so now also these are just some results that to show that some results are physically possible and some of them are physically impossible, because one of them interfere with the furniture and the other one does not. And so these are some of qualitative results. So given an image, then we will be able to synthesize. We can synthesize generate the pose. Okay, so yeah, so these are some additional results. One image, and then given this scene, we will be able to insert 3D pose in the scene realistically. Some failure cases. So here, without additional knowledge, then this is a sitting surface, but this is a stove, so we should not sit on that. But without additional semantics, then the model decides to put a person there. But and some of them there are still some problem with from time to time the object will be close to the furniture or intersect with the furniture a little bit, or without support. So these are the things we still need to improve. Okay, to summarize, so basically we developed 3D humans post synthesizer. So we leverage what we know with 2D and 2D data set and 3D data set, and so that we can generate a post synthesizer, and from that we will be able to learn what and where and what module to insert humans in the scene. Okay, so I'll just show some result for the next one. Okay, so basically I only have a few minutes, so I'll show that given if we hear some music, then you would probably know the kind of dance that you have in mind, right? So for that, we learn from mocap data from different dance, and we want from that we want to, and then from that we will be able to basically we learn from different dance, at least three dance style, and then we can basically take a Decompose-to-compose framework, which first decompose the poses into units, and then from that we can match the motion and bits, and then we can synthesize. We can combine them together and synthesize the new results. So again, I don't have time, so I'll just skip that. I'll show you some results first. Okay, so this just to show that we can match a moon. So now here we can synthesize results. So these are not in the training data. These are synthesized results based on different music. Given some piece of music, then we generate some dance movements. And from that we can also use some synthesizer to fresh out the real body from the mocap data to real images. Okay, and there is now a piece of work that I don't have time to talk about. So basically, it's about inserting video into video. So we can take one person and insert this person into the other scene. Likewise, we can take this car from this scene and insert into the other scenes. And here, we do not consider ground plane. So without knowing geometry, we just want to see whether we can insert the object into the scene so that there will be only a few artifacts. And there's an ongoing work that we have. We also work on human pose, as I mentioned, from single image. How do you estimate 3D pose and shape? And in addition, we also work on composite image synthesis. Say you have a number of images here, and how do you find? Say we want to compose a new scene based on this input. How do you synthesize new results? Okay, so that's all I have to say today. And so basically, the main idea is to understand 2D and 3D scenes so that we can synthesize human with respect to the context object, and in fact also about function. And I want to thank all the collaborators and students. Without them, I cannot get all this work done. Thank you.
Okay, so that's a very interesting talk by Ming-Hsuan. So the next is our QA section. Does anyone has some questions?
Yes.
Hi, yes. Yeah.
Yes.
Hi, Professor Yang. My question is, in your first work, can we use single chain model to insert different kinds of objects into the segmentation map?
So far we are not able to do that. We build one model for one particular object class, and because the shape variation is quite large, and so we don't. Yeah, I mean maybe you can try that, but we are not able to do that yet. So in that work, we train one model for person and one model for cars. So yeah, maybe you can have unified result. I don't know, but yeah.
All right. And my second question is in your second work, the geometric adjustment is very interesting and useful. And can you provide more details?
Oh, for that actually that's kind of a trick. That's not that difficult. Basically, we just look at, because we have 3D model, and we just use 3D correlation between poles and the furniture. And then if the correlation is not 0, that means there is some intersection. Then we just find the next the closest solution without any correlation. And so that's just we just use some heuristic for that. We don't have anything particular new. And I believe the code may be available now, and you can look into that too.
Okay, thank you.
Okay, so if anyone has other questions? Okay, I think we can go forward, and thanks again for your
Thank you.
talk. Okay,
Yep.
thank you. Bye.
Bye.